In this episode, we will talk about learning from peers in reasoning models.
Today's deep dive takes us into the fascinating world of large reasoning models, or LRMs for short. We'll be exploring how these, well, sophisticated AI systems can actually get better at tackling complex problems
That's so.
by learning from each other during the reasoning process itself. It's quite an interesting approach.
Right, because these LRMs, they're already pretty good at problem solving, aren't they? They can even self-correct to some extent.
You can, yeah. But this research highlights a really significant challenge they often face, something called the prefix dominance trap.
The prefix dominance trap. Okay, what exactly is that?
Well, it describes this tendency where if a model starts its reasoning process off with even a small error, just a little bit incorrectly, it
Uh-huh.
finds it incredibly difficult to get back onto the right track. It's like that initial incorrect thought, that prefix, just dominates everything that follows.
I think I get it. It's like, if you make a wrong turn right at the start of a long journey, it's really hard to correct later on, even if you realize the mistake.
Exactly. That's a great analogy. And the study found this has a huge impact. A model called QWQ32B, for instance, saw its performance drop by nearly 20%,
20%.
just from starting with the first 15% of an incorrect answer. Just 15%.
Wow. Okay, so that trap is a serious problem.
It really is. It shows that while self-correction exists, it's often not powerful enough to overcome a bad start.
So how do we help them get out of this trap? You mentioned learning from each other.
Yes, and the inspiration here is quite interesting. The researchers looked at psychological studies, specifically how we humans learn by interacting with our peers.
Ah, like group work, but for AI.
Sort of.
Yeah.
Led them to develop this concept called learning from peers, or LEAP, L-E-A-P.
Leap, okay. And the core idea.
The core idea is simple, really. Enable these LRMs when they're working on the same problem in parallel.
You mean running multiple attempts at once?
Exactly. Enable them to share their intermediate reasoning steps with each other. They get to see how the other peers are thinking as they go along.
So instead of working in isolation, they collaborate mid-process.
Precisely. Think of it like a team of scientists tackling a hard problem, sharing notes and partial findings as they work, not just comparing final results.
And this leap approach, did it actually work? Did it help?
Oh, absolutely. The results were quite remarkable. They saw significant improvements on some really tough benchmarks, things like the Amy Math competitions for 2024 and 2025.
Those are notoriously difficult.
They are. Also, the AMANO 2025, another math Olympiad, and GPQA Diamond, which is a graduate-level question-answering dataset. Very challenging stuff.
And what kind of improvements are we talking about?
Well, take that QWQ32B model again. With LEAP, it gained almost 5 absolute percentage points on average across those benchmarks.
5 points is substantial at that level.
It is, and get this, it actually outperformed a much, much larger model, the DeepSeek R1671B, on 3 of the math benchmarks.
A smaller model beat a bigger one just by using this leap method.
Correct, and there's more. They have a fine-tuned version, part of their LEAP-T series, the 7 billion parameter one.
So relatively small in today's terms.
Right. That LEAP T7B model managed to match the performance of a 14 billion parameter DeepSeek model on the AME 2024 benchmark.
Okay, that's genuinely impressive. Collaboration really packs a punch here. So our mission for this deep dive is clear then.
Yeah.
We need to understand how LEAP actually works, the mechanics of it, how it beats that prefix dominance trap, and what this all means for AI reasoning going forward.
Sounds like a plan. Let's start by revisiting that prefix dominance trap, the motivation for LEAP.
Right. You mentioned an experiment they designed.
Yes, a clever one.
Yeah.
They basically forced the models to start solving problems from a fixed beginning.
How?
They took the first 15% of the text from a previous attempt. Sometimes it was from a correct solution, other times from an incorrect one. Then they let the model complete the reasoning from that fixed start.
Controlling the prefix to see what happens.
Exactly. Does a good start help? Does a bad start hurt? And can the model recover from a bad start?
And the results confirmed the trap exists.
Unequivocally. As we said, that roughly 20% performance drop when starting with the bad prefix was consistent across different models, like the DeepSeek Distill Q in 7B and 14B and the QWQ32B. It really hammered home how vulnerable they are to those initial errors.
It really makes you think, doesn't it? It feels quite human. If we start thinking about something the wrong way, it can be really hard to shake that initial idea off.
It does resonate with our own experience, yeah. It highlights a fundamental challenge in building robust reasoning systems.
Okay, so LEAP is the proposed solution. You mentioned cross-path interaction and parallel inference. Can you break that down for us?
Sure. So normally when you want multiple shots at a problem, you run the model several times independently, right?
Yeah, generate maybe 10 different answers and pick the best one somehow.
Right. That's what they call independent reasoning.
Yeah.
You generate these parallel paths, maybe use self-consistency like picking the most common answer or some self-verification within each path, but they operate in isolation.
Got it. Each path is on its own.
Exactly. LEAP changes that. It introduces these things called LEAP blocks into the process. These blocks are points where the parallel paths actually interact and share information.
Okay, LEAP blocks. That sounds like where the magic happens. What goes on inside one?
It's a two-stage process, and it happens periodically, let's say every T tokens generated.
Key being some number you set.
Right, a hyperparameter. So stage one is summarization. Each reasoning path stops and generates a quick summary of its thinking so far.
Like a status update.
Kind of. A concise summary, maximum 256 tokens, just capturing the essence of its current reasoning.
And is it just a free-form summary?
No. And this is clever. It's guided by a randomly chosen summary trigger and template. You can see examples in the paper's appendix. The idea is to get variety in how they summarize, but still ensure the key points are captured.
Interesting. So you get diverse but structured summaries. Makes sense. What's stage 2?
Stage 2 is routing. Once all paths have their summaries, these summaries are shared with their peers. But crucially, how they're shared depends on the routing strategy.
Ah, so it's not just broadcasting everything to everyone.
Correct. They tested 3 main heuristic mechanisms for routing. It's about deciding which summaries a particular path gets to see.
Okay, what are the options?
First, there's dispersed routing. The intuition here is, if I might be wrong, I probably want to see ideas that are different from mine.
Right, get a fresh perspective.
Exactly. So dispersed routing sends each path the summaries that are least similar to its own current summary. They measure similarity using something called normalized Levenshtein similarity.
Levenshtein.
That rings a bell. Measures how different 2 strings are.
Precisely. It counts the edits needed to change one string into another. Normalized just puts it on a 0 to 1 scale. So dispersed routing aims for low similarity scores. It wants diverse inputs. Okay, that makes sense for breaking out of a wrong path. What's the next routing type?
The opposite, really. Clustered routing. Here, the idea is that if several paths are thinking along similar lines, maybe they're onto something correct.
Reinforce the consensus.
Exactly. So clustered routing sends each path the summaries that are most similar to its own. It tries to group and strengthen paths that seem aligned.
Okay. Dispersed for exploration, clustered for reinforcement. Is there a third?
Yes. Hybrid routing. As the name suggests, it tries to get the best of both worlds. It selects a mix. If it's selecting the top K summaries, it takes, say, K2 of the most similar ones, like clustered, and K2 of the least similar ones, like dispersed.
So, a bit of reinforcement and a bit of exploration together.
That's the goal. Trying to balance confirming potentially correct paths with injecting novel ideas.
And they use that normalized Levenshtein similarity for all these comparisons.
Yes, that was the metric used to quantify similarity between the summaries for routing decisions. It's calculated as 1 minus the Levenshtein distance, divided by the length of the longer summary. Simple, but effective.
Okay, so we have these LEAP blocks. Summarize, then route based on similarity using dispersed, cluster, or hybrid. The big question, does it actually work against the prefix dominance trap?
The evidence says yes, quite convincingly. Figure 4 in the paper shows the results when they ran the bad prefix experiment again, but this time with LEAP enabled.
Did the performance gap shrink?
Significantly. Across the different models, 7B, 14B, 32B LEAP consistently reduced that performance hit from the bad start. Remember the DeepSeek-distilled Quinn 14B model? Its gap dropped from almost 20 points down to about 8 points with LEAP.
Wow, from 20 down to 8. That's a huge improvement in recovery.
It really is. It strongly suggests that seeing what your peers are thinking, even if you started wrong, gives you a much better chance of correcting your course.
And did it only help when starting wrong? Or did it affect performance from good starts too?
That's another interesting finding, actually. Appendix B shows that LEAP also improved performance even when the model started with a correct prefix.
Really? Why would that be?
Well, it suggests LEAP isn't just about fixing major initial errors. It might also help catch or mitigate more subtle errors that could creep in later in the reasoning process, even if the start was good. It seems to generally make the reasoning more robust.
So benefits all around, potentially. Okay, that's the trap sorted. But how does LEAP perform overall on those really hard benchmarks you mentioned?
They did a comprehensive evaluation, AMY 2024, AMY 2025, AMO 2025, GBQA Diamond. They used standard metrics like pass at 1, getting it right on the first try, and also cons at n, looking at consensus among multiple tries.
And they tested the different models and routing strategies.
Yes, the DeepSeek Distill QN 7B and 14B, QWQ32B, they carefully controlled the token budgets too to make sure comparisons were fair.
And the main takeaway?
The main takeaway, shown clearly in Table 1, is that models with LEAP consistently beat the baseline models, the ones doing independent reasoning, across all benchmarks, given similar amounts of computation.
Can you give an example?
Sure. The DeepSeek R1 Distill Quinn 7B model, the smaller one, when using top 4 dispersed routing.
Meaning it looked at the 4 least similar summaries.
Correct. It improved by an average of about 6.5 percentage points across the benchmarks compared to its baseline. The 14B model saw a similar gain, around 6 points.
And you mentioned QWQ32B with LEAP beating the giant 671B model.
That's right. QWQ32B with top 4 dispersed routing outperformed DeepSeek R1 671B on all 3 math datasets, averaged about 3.3 points higher. Shows the power of this collaboration.
What about the routing strategies themselves? Did one consistently win out?
Generally, yes. Dispersed and hybrid tended to perform better than clustered.
Which suggests?
It suggests that getting those diverse perspectives, the ones dispersed routing prioritizes, is perhaps more valuable overall than just reinforcing paths that already agree. Exploration seems key.
And the number of summaries. Did looking at more help top K?
Yeah, generally moving from looking at the top 2 summaries to the top 4 summaries improved performance.
More perspectives are better, up to a point.
Exactly. But as we'll touch on later, there seems to be a sweet spot. Too many summaries might actually hurt performance.
Okay. And what about consensus? Did LEAP help there too?
Yes, the appendix shows LEAP also led to better results using consensus scoring, cons at n, compared to standard voting methods on the baseline outputs. It helps the different paths converge more effectively towards the right answer.
Okay. Better accuracy, better consensus. But what about the cost? All this summarizing and routing must use more tokens, right?
You'd think so, wouldn't you? But the analysis showed something quite surprising.
Oh.
Looking at token usage, LEAP didn't significantly increase the total number of tokens generated. And in some cases, like on the GPQA benchmark, it actually reduced the token count slightly.
Reduced it? How is that possible?
Well, the thinking is that the efficiency gained by correcting errors earlier or converging faster to the right answer might actually outweigh the extra tokens used for the summaries and communication. Less wasted effort exploring dead ends.
That makes sense. And they also looked at aha moments.
Yeah, those points where a model seems to suddenly realize it made a mistake and corrects itself. LEAP actually led to fewer of these moments.
Fewer? Why is that good?
It suggests that the peer input is helping the model stay on track or correct course more gradually earlier on. They don't need as many of those big, dramatic, potentially costly self-corrections later in the process. The peers provide the nudge sooner.
Interesting. So better accuracy, often similar or even slightly less computation. That's a compelling package. Now, you also mentioned leak T. What's the T for?
The T is for trained or fine-tuned. The researchers noticed that the smaller models, like the 7B parameter ones, sometimes struggled a bit with the LEAP framework.
Struggled how?
They weren't always great at writing useful summaries. Or sometimes they didn't seem to effectively use the summaries they received from peers. It's like they didn't quite get the collaboration aspect intuitively.
Understandable for a smaller model, perhaps.
Right. So to fix this, they created the LEAP series. They took their 1.5B, 7B, and 14B models and specifically fine-tuned them to be better at performing the tasks within the LEAP framework, summarizing well, integrating peer feedback effectively.
How did they fine-tune them? What was the training data?
They generated data using a bigger, more capable model, the 32B DeepSeek, running with LEAP. They then filtered these runs, keeping only the examples where LEAP led to a correct final answer, and the intermediate summaries were good, concise, and informative.
So they created examples of good collaboration leading to success.
Exactly. Then they used this curated data set to fine-tune the smaller models, essentially teaching them how to collaborate effectively using examples from a better collaborator.
And did this fine-tuning work?
It worked very well. Table 2 shows consistent gains for the LEAP-T models across the board on the math benchmarks, in both pass at 1 and consensus metrics. That LEP T7B model we mentioned earlier, matching the 14B baseline, that came out of this fine-tuning.
So, specific training for collaboration really boosts the effectiveness, especially for smaller models.
Definitely. And Figure 6 shows that these LEAP team models also scale better at test time. As you generate more parallel responses, the LEAP team models make better use of that extra computation compared to the baseline models.
They also compared this to just standard distillation, right? Like
Yeah.
just training the small model on the outputs of the big model.
Yes, and that's a key point. Simple distillation, without the LEAP framework involved in the training data generation, didn't give the same performance boost.
Meaning,
Meaning, it's not just about learning what the bigger model knows, it's about learning how to work within the LEAP collaborative structure. The fine-tuning for the peer learning process itself seems crucial.
data. Okay, let's dive deeper into the leap mechanisms themselves. They looked at communication sensitivity.
Yes, basically how sensitive the performance is to how the communication happens. First, the frequency, the granularity T, the token interval between LEAP blocks.
What did they find? Communicate more often.
There was a trade-off. Communicating more often, smaller t, gave a slight accuracy boost, but it also used more tokens because you're summarizing and routing more frequently.
Makes sense. A cost-benefit balance. What about the amount of communication? The traffic or topco?
Right, how many peer summaries does each path look at? We
Yeah.
touched on this. Figure 8 shows that for the 14B model, performance improved going from top 1 to top 4,
Uh-huh.
but then it actually started to dip slightly and became more variable beyond top 4.
So more isn't always better there either. Information overload?
Seems likely.
Eh.
There's a sweet spot. Enough diverse input is good, but too much might just add noise or confusion, like being in a meeting with too many people talking at once.
Huh. Yeah, I can relate to that. They also looked at when communication is most useful.
Yes, the evolution tendency. They categorize the effect of communication. Did it keep a path consistent, leave it unaffected, or actively influence it? Figure 9 shows the influence was strongest in the early to middle stages of reasoning.
So early interventions have more impact.
It appears so. Once a path gets really far down a line of reasoning, it might be harder to change its course significantly. Early peer feedback seems more effective.
And they confirmed this by testing just a single communication point.
Yes, the communication position experiment. They tried LEAP with just one block, placed at different points. The results in Figure 10 and Tables 3 and 4 showed that a single early communication step around the 4,000 token mark in their setup gave the biggest bang for the buck.
Okay, so the takeaway is communicate relatively early, don't overdo the number of peers you listen to, and maybe don't communicate too frequently if you're worried about token cost.
That seems to be the practical guidance, yeah.
All right, what about robustness? How well does LEAP handle messy situations? They did a post hoc robustness analysis.
Right? First, error tolerance. They deliberately mixed good and bad starting paths. What happens if most of your peers actually start out wrong?
I'd assume that would be bad. Garbage in, garbage out.
That's the intuitive assumption. But Figure 11 showed something remarkable. LEAP still outperformed the baseline even when all the initial paths were incorrect.
All of them. How?
It's quite surprising. It suggests that even from multiple flawed starting points, the models, through interaction and their own underlying capabilities, can sometimes find their way. Maybe they extract useful fragments of reasoning, or the interaction helps them identify shared flaws more quickly. It shows impressive resilience.
That's really counterintuitive, but very encouraging about the method's robustness. What else did they test for robustness?
They looked at performance across different difficulty levels. They split the AMY 2024 problems into 5 bins, from easy to very hard based on how the baseline model did.
And LEAP helped across the board.
Yes. Figure 12 shows LEAP, and LEAP-T improved accuracy on all difficulty levels. Crucially, they even got some answers right on the very hard problems, where the baseline completely failed scored 0.
So it's actually pushing the boundary of what these models can solve.
It seems so. And interestingly, on the harder problems, LEAP often used fewer tokens, excluding summary tokens, suggesting it helps them find the solution more efficiently when the search space is tough, less flailing around.
To get a feel for how it helps, they did some human verification case studies.
Exactly. They looked closely at specific examples. One detailed case study was AME 2024 Problem 11, comparing QWQ32B with and without LEAP.
What did they see?
A big jump in correct answers from 25% correct without LEAP to 62.5% correct with LEAP. And when they looked at how the answers changed,
Yes.
a lot of the incorrect answers became correct. But importantly, no correct answers became incorrect.
So it's primarily helping, not hurting. It's a corrective mechanism.
That's what the evidence strongly suggests. It guides towards correctness without messing up paths that were already on the right track. The appendix has more examples too, showing things like smaller models failing to summarize well, or cases where peer interaction clearly fixed an error.
Fascinating to see it working at that granular level. Okay,
Yeah.
finally, how does LEAP stack up against other related work?
Well, they acknowledge work on the self-correction bottleneck, and they contrast LEAP with simpler parallel methods like self-consistency or best of n, where there's no interaction during reasoning.
Right, LEAP's key is that mid-process interaction.
Exactly. They also compare it to other multi-agent approaches, like mixture of agents, MOA.
What's the main difference there?
The key difference highlighted is the granularity and timing of interaction. MOA often involves agents working for a whole round and then sharing only their final output of that round. LEAP allows this more fine-grained sharing of intermediate summaries periodically throughout the reasoning process.
So LEAP gets more detailed, real-time updates from peers.
That seems to be the distinction they draw. And they mention in the appendix that MOA didn't seem to work as well for these standard LRMs in their setup, perhaps because of this difference in interaction style.
Okay, that makes sense. LEAP's continuous summary-based sharing seems unique.
It appears to be a key differentiator, yes.
All right, let's try to wrap this up. What are the main takeaways from this deep dive on learning from peers?
Well, first, the prefix dominance trap is real and significant. Starting wrong really hurts these models. Second, LEAP is a very effective solution. It leverages peer interaction during reasoning to overcome this trap and significantly boost performance on tough benchmarks.
And it does this often without a major increase in computational costs, sometimes even reducing it.
Right. Plus, the fine-tuned LEAP-T models show that we can train models specifically to be better collaborators, which is especially helpful for smaller models.
And some of the really surprising bits.
Definitely the extent of that prefix dominance trap. Also, LEAP's ability to learn, even from flawed peers, that robustness was quite striking, and its success on problems where the baseline completely failed.
It really pushes the envelope. So a final thought for our listeners to chew on.
Maybe think about the implications of this kind of collaborative intelligence. We see it works for AI, helping them overcome individual limitations. How do the principles behind LEAP sharing intermediate work, valuing diverse perspectives, structured communication, apply to how we learn and solve problems in teams? Could we be more effective collaborators?
That's a great question, applying AI principles back to human interaction. Interesting. Did the paper suggest where this research might go next?
Yes, they mentioned two promising directions. One is extending this peer learning idea into reinforcement learning frameworks. Could agents learn collaborative policies this way?
Okay. And the other?
Exploring learning from peers that have different specialized expertise. Maybe one peer is good with certain tools, another with a specific type of reasoning. Could they combine complementary skills through LEAP?
Like assembling an expert AI team that collaborates effectively. Very cool possibilities.
Definitely exciting avenues for future work.
Well, this has been incredibly insightful. Learning from peers seems like a really powerful concept. For you, the listener, if you want to explore further, we'll have links to the paper, the code, the data, and the models in the description. Thanks for joining us on this deep dive.